Thank you. Good afternoon, everybody. I'm Manoj, and I'm a third-year PhD student. And today we had a very good discussion on water quality in reservoirs, and most of the nutrients that is coming to the reservoir is from the catchment. So today we'll be discussing about the catchment modeling, and and this is one of the part of my PhD project, and we are using the catchment modeling tool SWAT. It's eco-hydrological model, and we are using it for simulation of flow and nutrient loadings in the Onkaparinga catchment. And yeah, we know that Onkaparinga catchment is a very important source of drinking water supply to metropolitan area of Adelaide, and this catchment is not protected. It's open catchment, so it is open for private and public use. So there is a lot of human activities such as horticulture, pasture, agriculture, and all of those things. And because of those practices, we have there is a risk that the excess amount of fertilizer that we use, they will reach to the water bodies ultimately. And we have got these reservoir, Mount Boulder Reservoir, which is a storage reservoir, and Happy Valley Reservoir, which is a water supply reservoir. And because of the excessive fertilizer, there is a risk of eutrophication of water bodies, and it can lead to algal blooms, and it will always have high treatment cost, and that's the reason why our water bills are never decreasing. It's always increasing. So how can we inform better catchment management? So if we are able to provide some information regarding identification of the hotspot of nutrient loadings, then that could be one of the solution. And another thing is we can determination of best management practices, such as where to put the sedimentation pond or where to put the wetland treatment system would actually reduce the nutrient load. That kind of information would be really helpful. And another thing is how the water quantity and quality will change in the future because of the climate and land use change. So if those information are there, then it will be very helpful. And for that purpose, most of the time we use catchment modeling, and it is a widely used process. So our catchments are very complex system. We have a lot of processes inside the catchment. So we have rain, and then there is evapotranspiration, there is exchange of water between stream and the groundwater. So we have rural areas and urban areas, and because of all of these complexities, we have a very complex process. And when we are using the models, our models should actually represent these complex processes. And one such model is the SWAT. It is Soil and Water Assessment Tool developed by USDA from America, and it is publicly available, and it is a process-based catchment model. So I talked about the different processes before, and then these processes are represented by this model, and it is a semi-distributed model. So semi-distributed means it will provide simulation not just at the outlet of the catchment, but also several points within the sub-catchment. And this is a fairly complex model, and we require a lot of different input data. So we require climate data, and it can be available from Bureau of Meteorology and SILO. So scientific information for landowners developed by or managed by the Queensland government. And we require maximum and minimum temperature, rainfall, and other parameters. And similarly, we require a lot of soil information, such as soil texture, plant available water capacity, and a lot of other 14 or 15 parameters. And this can be obtained from the ASRIS, Australian Soil Resource Information System. And we also require the land use map and the management operations, such as application of fertilizer and irrigation. So because we are using this land use, and it has got vegetation, and vegetation has some influence on on the water balance. So we call it eco-hydrological model. And so how do we begin with, how do we configure the model and run it? So for that process we need digital elevation model, land use map and soil data along with the climate data, and from this digital elevation model, which is a 30-meter resolution map, from this we can divide the catchment into sub-catchment so that so that the model can actually simulate the data at the sub-catchment level. And this sub-catchment can be further divided into hydrological response unit from the combination of slope, land use and soil. And once all of these processes are done, we develop a model, we have a model, and then we run it, and then we can get beautiful graphs in the end, or we try to get beautiful graphs. And so this is the SWAT process that I mentioned earlier. The catchment is divided into sub-catchment and then further into hydrological response unit, which is the combination of soil type, land use and slope. And this is the fundamental unit where the flow, sediment and pollutant loads are actually estimated. And then once they are estimated, they are summed across the sub-catchment, and after that they will be routed through channels, and if there is any ponds or reservoir, then they will be routed through those kind of water bodies, and then finally at the watershed outlet. So for model calibration and validation, most of the model has to be calibrated, and we took 10 years of data for calibrating from 2000 to 2009, and for validation we took 4 years. And the model was calibrated for flow, total suspended solids, total nitrogen, and total phosphorus loading on monthly basis. And we also estimated the uncertainty in the model. And to get the better, when we are doing the catchment modeling, we always want to get the improved modeling system. So for that purpose, we devised two approaches of calibration, and one of them is single site calibration. So single site calibration means we just use data from only one station for the whole catchment, and on the basis of this we develop the model. And in our case, what we did is, for single site calibration, we calibrated the model on the basis of these outlet Hall graphs, and then this is further tested at different substations. And another approach is multi-site calibration. So in multi-site calibration, what we are doing is we'll be using every data available over here, and then finally we develop the ultimate model, and this we term as multi-site calibration model. And then to compare between which calibration approach is giving us improved modeling process or improved model, we took 3 performance criteria. One of them is R square, coefficient of determination, Nash coefficient, and percent bias. So generally R square and NS should be greater than 0.5, and we see that for flow, the single site calibration is performing better than multi-site calibration, but in case of total nitrogen and total phosphorus loading, we can see that these blue numbers, they mean that they meet the satisfactory criteria for the model. So from these two comparison, we see that multi-site calibration is good for total nitrogen and total phosphorus loading compared to the single site calibration. And these are some of the graphs. So I want to focus on the total nitrogen and total phosphorus loading, and basically we see that total phosphorus, the performance criteria of multi-site calibration for total nitrogen and total phosphorus is much better for multi-site calibration compared to single site calibration. And here in Algate, which is the urban sub-catchment, we can see that the timing is not matching, and that's why we have very low NSE compared to the multi-site calibration. And similarly for the total phosphorus, we have just 0.06, but over here it has been significantly increased. And this one is for the validation period. and even in the calibration we have improved result. And finally at the whole graphs we have similar result. So this suggests that we have, this suggests that multi-site calibration is much better. And we also looked at the uncertainty analysis, and then here the green band over here suggests how it helps to quantify the uncertainty. And here in the multi-site calibration we can see the thickness is very high. So this suggests that the multi-site calibration, or we can say that single-site calibration gives less uncertain model simulation. But in case of total nitrogen, this green band is quite less. So this suggests that the model, this suggests that multi-site calibration gives less uncertainty compared to single-site. Over here we have got highly uncertain total nitrogen simulation, and this is represented by R factor. R factor is comparatively less than single-site, and similarly for total phosphorus we can see that this R factor has been reduced. So multi-site calibration will attempt to give uncertain simulations. And after calibration of the model, we can visualize how the nutrients and I just want to run the animation. So after calibration we can see how the flow or nutrients they vary within the catchment. So this suggests that for different period of time we can see different loadings. So sometimes it's red over at the outlet, so it's and this is the color coding for the 12 phosphorus. So generally it helps to identify how the nutrients are traveling inside the subcatchment and at what particular point of time. So, and this is just a snapshot for the year 2005 for June, and then here it gives us the spatial and temporal variability. And to conclude, SWAT proved to be a suitable modeling tool for the arid rural Onkaparinga catchment for flow and nutrient loadings, and it can also be applied for other catchment of Australia. And from single-site and multi-site calibration, we find out that if we have more number of gauging stations, then there is chance that we can improve model. And our future work would be to analyze the scenarios of how water quantity and quality will change because of the land use and global climate change, and it is underway. And we are also applying SWAT in Torrance catchment by one of our team member, Miss Hannah. So she is inside the room. And finally, after all of this conclusion and future work, I want to show how we do computer modeling. So how to do computer modeling. So this is one of the many ways we can do computer modeling. And sometimes it is not always boring, it's sometimes fun. So finally, I would like to acknowledge my research team and the SWAT for providing financial and logistic support. Thank you.